So the emphasis here is on the fact that back here we noticed that we could just end up taking 5 minus 3, and that was a shorter way to get the answer of 3 to the second. In this particular instance, we noticed that when we canceled things out, we ended up with 1 over 3 squared, or 1/9. But when we subtract 3 minus 5, 3 to the 3 minus 5 would actually be 3 to the negative second power. So we're saying that if we do it the way we had on the previous page, we get 3 to the negative second. But whenever we reduce it, we get 1/9. So that must actually mean that since we've come up with these answers in two different ways but using the exact same problem, that must mean that, well, look at the relationship between these two. That 3 to the negative second actually is saying 1 over 3 to the positive second. So what happened here? Well, if you put it over a 1, you notice that really the fraction just basically reciprocates. We call this a reciprocal whenever we flip the fraction. And in order to do that and still maintain the same value, because obviously 3 to the negative second is not the same thing as 1 over 3 to the negative second, so we notice that we can end up changing the sign, because 3 to the negative second ends up being 1 over 9, which is 1 over 3 to the second. In your calculator, you'll also notice that if you enter that in, 3 raised to the negative second power, you do get 0.11111, which is the same thing as 1 over 9. And this is true for any example. So if we take 7 to the 12th over 7 to the 93rd power, well, we should end up getting 7 to the 12 minus 93. 12 minus 93 is negative 81. And so 7 to the negative 81 should give me the same thing as, now it's a very ugly number, should give me the same thing as 1 over 7 to the positive 81. So basically, if we put this thing over 1 and we flip it, change the sign, 1 divided by 7 to the positive 81st, notice just by inspection that those two numbers are exactly the same thing, which is the same thing we would get if we took 7 to the 12th divided by 7 to the 93rd. And notice that we still get the same answer that way, but our goal was to try to reduce it to something a little bit less complex. Now, in some of maybe the algebra classes you took in the past, you've seen some nightmarish things that might have looked like this: 3 to the 3rd, x to the 7th, y to the 6th, z to the 14th times x to the 13th times y to the 5th. Now, if you take this piece by piece or very slowly, you could very well simplify it down and get it to something that looks a lot prettier. But in reality, how often do you run into something this ugly? What I'm trying to say is that I emphasize how important it is just to have a basic conceptual understanding of these several basic ideas that we have here. And as one last rule, I will go ahead and just put in our little rule, I will also write that if we take x to the a over x to the b, we get x to the a minus b. Similarly, x to the negative a is equal to 1 over x to the positive a. And then that also holds, that's identical to saying this: 1 over x to the negative a is equal to x to the positive a over 1. So basically, to change a negative to a positive exponent, you can flip the fraction and change the sign. So these are a set of rules, or this is a set of rules. However, I don't really encourage you to memorize the rules. You're going to find yourself getting into trouble later on, because memorizing things is never a good way of learning, and it doesn't emphasize the conceptual importance of what's taking place. So rather than to memorize these so that you can do big, ugly, complicated problems like this one, I'm asking you to understand the basics and to not have to worry about applying any rules to big, ugly situations like this.